All right, so now we're going to go with a concrete example of how to use atomics to do something, and we're going to evaluate the value of pi numerically, and we're going to do it using this nice little diagram. So what I have is a circle inscribed in a square, and the circle has a radius r. So we know that the area of the circle is pi r squared, and we can guess that the area of the square is 2r times 2r, so 4r squared. And what this means is that pi, if we take these two expressions, pi is 4 times the area of the circle times the divided by the area of the square. And what we can do on the CUDA side, if we're doing a Monte Carlo evaluation, is we can generate a large number of random points within the square. So we fill up the square with a large number of points, and then we can't count the number of points that end up inside the circle, because we can easily do the radius and just see if the distance of this circle from the center is less than the radius. Then we're inside the circle, and then we can sort of estimate pi as being 4 times the number of points in the circle divided by the total number of points. All right, so let's now try and calculate the value of pi using Monte Carlo method and atomics as well. So let's call this Monte Carlo Pi. All right, as always, I will wipe everything out and explain once again how everything works. So let's get started at this location. Right, we do want a couple of headers. We do want the courand for one, include courand.h, and we also want IO stream. We want IO manip, which is going to be used for setting precision. And that's about it for now. Okay, so let me explain what's going on here. We're going to generate a rather large number of points. Let's have count equal to, I don't know, 512 by 512. There we have it. And then constant size would be count times size of float. Let's use floats for this example. Okay, so let's have some CUDA status variables. So CUDA error underscore t. CUDA status, then we'll have courand status t, courand status, and then we'll have courand generator t, which is gen. Oh, made a spelling error there. Rand, there we go. Courand generated t. All right, so we want to use the courand libraries to initialize a huge array of 512 by 512. Well, it's a one-dimensional array of points. So courand status equals courand create generator, and we want to initialize the gen value, and we're going to use courand png sudo. So same stuff as we were using before, which the Mercent Wisdom might not be the right one for this example, but it doesn't really matter. Just trying to demonstrate this. So courand set sudo generate a random seed. So we set the seed from, let's take time 0. There we have it. Okay, so what we need to do here is we need to initialize two arrays, an array of x coordinates and an array of y coordinates. And both of them would be of size count, surprisingly enough. So let's have float x and float y. And then we'll just do CUDA status equals CUDA malloc for x with the size, and then just duplicate this and do the same for y as well. All right, so we've initialized the two arrays. These are the two x and y values that we're going to take the results from, and then we will generate some random uniform data for them. So courand status equals courand generate uniform. So uniformly distributed variables from the generated gen go into x, and their sizes count, and we do the same for y as well. So we've got the x and y coordinates, and now we can just count the points. So I'm going to count points with the 512 by 512 layout, with values of x and y. Don't worry, I'll create the kernel in a minute. Meanwhile, we want to get the overall count. It's actually, we're going to, well, let's introduce a device variable once again at the top. Now, we've done this in a previous example where it went wrong, but here it's going to be just fine. So device int d count equals 0. And that's where we'll keep the total number of points that we subsequently need to copy into h count. All right, so let's do that. That would be go to memcpy from symbol into h count from d count size of int. So just a single int with a number of points. Then we could have free x, we could have free y, and then we can actually output the final result. And the way we can do it is with that set precision call. So cout, I'm going to set precision to 12, and then say pi is approximately, and what is it? So remember, we have to do 4.0 times the number of points, so h count in this case, divided by the total count. Also cast to float. There we go. And end line, get char, turn 0. Okay, so all we have to do now is look at the kernel and how that would actually work. So we have x and y coordinates where x's and y's go from 0 to 1. So let's start writing this. Global void count points. So what we get is const float x's and const float y's. And then let's get the index. So in this case, index will not just be the thread ID within the block, but it would rather be block index times block dim.x plus thread index.x. There we go. And then we would have the values of x and y. So x is at idx minus 0.5f. Let me explain why this is done. So we've generated lots of values from 0 to 1, but it's easier to take 0, 0 as the center of the circle. So we just move everything by 0.5, and then it's easier to sort of evaluate the radius. So let's do the same for y. So it's y is at idx minus 0.5f again. All right, so we've got the x and the y, and then we want to determine the determine the value that will be either a 1 or a 0, depending on whether we're in the circle or not. And the way we can do it is say n equals, and then we do the square root, sqrtf, note the f prefix, that's for floating point numbers, and then we just do x times x plus y times y. And then we say that, well, if this is greater than 0.5, then we are outside the circle, so give us a 0. Otherwise, we are inside the circle, so give us a 1. So we get either a 0 or a 1, and now we can do the atomic operation to increment or not increment the dcount variable. So we just say atomic add dcount with the value of n. And that's it. So that's how it works. Let's try actually compiling it, see if it... Nope. Plenty of problems because you remember this atomic add business. We need to configure the project once again. So I'm going to jump in here and once again do compute 12 SM12. Let's press OK. Let's try this one more time. All right, still plenty of problems here. Let me just jump to a few of them. So forgot a curly brace here. All right, finally, there's just a semicolon that's missing from somewhere. Yeah, this calculation is not entirely correct. Oh, there's another thing that we forgot to include, which is the reference to kuran.lib. Remember, you have to have to basically add these to the listing, otherwise it's not going to work. So courand.lib, like so. And we're good to go. All right, so let's take a look at this value. Well, it's not exactly pi, but it's close enough given what number of inputs we had. So this is just a small demo of the kind of things that you can do with atomics, but with just one operation, we managed to effectively perform a Monte Carlo simulation.